Welcome, everyone. Today, I'm thrilled to introduce CUDA Agent, large-scale agentic RL for high-performance kernel generation. This project, a collaborative effort between ByteDance Seed and the Institute for AI Industry Research at Tsinghua University, tackles a massive challenge in AI development. Our overarching goal here is simple but ambitious. We want to transform large language models from passive code generators into active, autonomous systems optimizers. Let's look at the current bottleneck in AI infrastructure. If you ask a standard LLM to write a general Python script, like a Fibonacci sequence, it shows human-level proficiency. But, as you can see on the right, if you ask it to generate high-performance CUDA kernels, it fails utterly. GPU kernel optimization is foundational to modern deep learning, but it demands arcane hardware expertise. Right now, even the best LLMs remain uncompetitive against static compilers like torch.compile. To fundamentally solve this, we built CUDA Agent. To improve an LLM's intrinsic optimization ability, we constructed a large-scale training system resting on three complementary pillars. First, a scalable data synthesis pipeline to generate diverse RL tasks. Second, a skill-augmented, hack-proof agent environment. And third, algorithmic stability techniques featuring multi-stage RL warm-ups to prevent the model from collapsing during training. Let's dive into Pillar 1. Reinforcement learning requires a massive, diverse corpus of tasks to succeed, but we immediately hit a roadblock, the data scarcity problem. Look at the scales here. Base LLMs are pre-trained on trillions of tokens. However, public datasets of expert-level reference CUDA code are virtually non-existent because they are prohibitively expensive to manually write. This creates a massive bottleneck for fine-tuning. To overcome this scarcity, we engineered a scalable, three-stage data synthesis pipeline. First, we mine basic operators from PyTorch and Transformers libraries. Next, we use LLMs to perform combinatorial synthesis, essentially fusing multiple operators together to generate complex tasks. Finally, we run strict, execution-based checks using a custom rubric to ensure the tasks are executable, non-random, and represent a reasonable, non-trivial workload. The result? A perfectly curated dataset of 6,000 unique, high-quality training tasks. Moving to Pillar 2, we had to address the fact that LLMs need to compile, test, profile, and debug iteratively, just like human engineers. So, we built a React-style agent loop. We equipped the agent with real developer tools like Bash and multi-edit, guided by a strict skill.md workflow document. The agent analyzes bottlenecks, implements custom CUDA operators, and then compiles and evaluates them in a dedicated pool of 128 H20 GPUs. Based on the profiling feedback, it refines the code and loops again. A critical part of this environment is defeating reward hacking. If you just give an AI a naive speed-up reward, it will hack the system, learning to generate useless kernels or exploiting easy tasks to show false optimization, resulting in wild reward fluctuations. Our sub-innovation here is a normalized, robust reward schedule based on discrete milestones. An agent gets a score of 1 for mere correctness, a 2 if it's 5% faster than eager execution, and a top score of 3 only if it is 5% faster than both eager and torch.compile. We also protect this with strict file permissions to prevent any cheating. Now, for Pillar 3. When we first started reinforcement learning trials, the training completely collapsed after just 17 steps, as you can see on this chart. Why? Because of a severe domain distribution mismatch. CUDA coding data accounts for less than 0.01% of standard LLM pre-training data. This gap results in wild gradient fluctuations and massive variance during optimization when the model tries to sample low-probability tokens. To stabilize the model before Agentic RL even begins, we introduced a multi-stage warm-up solution. We split the process into zones. After a single-turn warm-up, we use rejection fine-tuning, RFT, to initialize the actor model, retaining only high-quality, positive reward rollouts. Simultaneously, we use value pre-training to initialize the critic model, which allows it to immediately provide accurate feedback on state sequences. The result is beautifully stable PPO optimization for the full 150-step run. Let's look under the hood at why this works. Without RFT, the policy's entropy explodes, the model becomes diffuse and incoherent, generating nonsense. RFT locks the agent into a structured output distribution. Meanwhile, without value pre-training, an uninitialized critic fails to penalize useless search paths, leading the agent into infinite, redundant interaction loops. Pre-training solves this, keeping the response length perfectly clipped. So, how does it perform? We put CUDA Agent to the ultimate test. The arena was KernelBench, featuring 250 distinct operator tasks evaluated strictly across 3 difficulty levels. Our goal wasn't just to pass correctness checks, but to achieve maximum execution speedup. We pitted our agent against the titans of the industry, Claude Opus 4.5, Gemini 3 Pro, and the static compiler torch.compile. The results were incredible. CUDA Agent absolutely shattered the static compiler baselines. We achieved a 100% faster rate versus torch.compile on level 1 tasks, and another 100% faster rate on level 2 tasks, achieving a 2.80x speedup. Even on the hardest level 3 tasks, we outperformed the compiler 92% of the time. Because traditional compilers rely on predefined rules, they simply cannot see the hardware-specific memory access and tiling strategies that our CUDA agent discovers dynamically. When comparing against proprietary giants on the hardest split, level 3, general-purpose models write naive kernels, but our specialized RL creates highly optimized systems. Claude Opus 4.5 and Gemini 3 Pro hovered around a 50% and 52% faster rate respectively. CUDA Agent reached 90%, outperforming them by roughly 40% in execution speedup, while maintaining a massive 94% overall pass rate on these highly complex tasks. This success is deeply synergistic. Removing any of our 3 pillars causes critical failure. Without the agent loop, performance drops to just a 14.1% faster rate, actively regressing. Without the robust reward, the agent hacks easy tasks and speedups drop heavily. And without RFT and pre-training, the training collapses entirely. Only the full CUDA agent achieves the 96.8% overall faster rate and a 2.11x geometric mean speedup. The big takeaway here is profound. LLM-based kernel generation is no longer just a novelty, it is now a competitive, superior alternative to traditional compiler-driven optimization. By combining scalable data, structured environments, and stabilized reinforcement learning, we are evolving foundation models from passive code generators into active, autonomous systems optimizers. Thank you.